Hi everyone, welcome to my YouTube channel again. And today I'm going to continue talking about the depth of focus and NA, which stands for numerical aperture. In the previous class, I talked about the DOF, depth of focus. So when we want to make the NA value high, you just have to think that NA is just the radius of camera lens. So if we make the NA high, there will be a lot of light coming in and the DOF will get lower. So the energy could not get into the place that we want to make a contact in it. So because of the DOF getting lower, the CD value will get low. On the other hand, if we make the NA value low, the DOF will get high and the energy will get to the target point and the CD value will get high. So here is just a diagram for the NA. You can see when it is 0.3, the radius of a camera lens is very small. However, when the NA is high, equals nearly about 0.8, the radius is large enough. So our target is to make a very small nanometer pattern. So we have to make the CD value small. Because there needs to be a lot of photons coming in. As you can see here from the equation, NA equals to n sine theta and CD equals to K1 lambda over NA. This is an equation for Rayleigh equation. If we want to make the CD value small, we have to make the NA as large as possible. So if the lambda is short, then the energy will get high. So the NA value will get high and the CD value will get low because of the Rayleigh equation. As you can see here, if the NA gets low, the CD value will get high. So there are some trade-offs between the CD, DOF, and the NA value. And later I'm going to give you a solution for this trade-off. We use off-axis illumination for it. We call it OAI. And I'm going to talk in the next slide. So we made every parameter optimal size to make the CD value small. However, we could make the CD value much more smaller to make into nanometer lithography. So I mean the fabrication. So I want to introduce you about the immersion lithography. We made every parameter as small or large as possible to make the CD value small. However, there is one more thing that we can make the CD value small. CD equals to K1 lambda over NA, as I talked to you before, the Rayleigh equation. And if we solve the equation, CD equals to K1 lambda over N over sine theta. As you can see here, we cannot change the parameter K1, NA, or lambda. So there is only one thing that we can change is by using N, the refraction rate. So in the immersion lithography, we use different refraction materials such as like glass or water to make a difference between them. And we use the 193 nanometer ARF to make the CD value much smaller. Now I'm going to talk about the CD-SEM, which is a device to measure the CD value in the material. So how we measure them, we use CD value. So if the light comes in and there will be a lot of refractions in it, and whenever the refraction rate changes and the space between them equals to CD, and we use it by scanning electron microscope to measure the CD value. So the difference between the refraction rate is equal to CD, so we use the CD SEM to measure them. As you can see here, there are a lot of light sources such as ultraviolet or IR, infrared, or EUV, or else. This is just a diagram for you to make sure you know it. These days we usually use ARF excimer laser 193 nanometer light, and we often use the F2 excimer laser 157 nanometer. Just you have to know them. And there are some important lights, which is the EUV, extreme ultraviolet. It is a 13.5 nanometer. And now I'm going to introduce you with the EUV equipment that usually ASML is the top scorer in this field. So how does the EUV equipment works? We use a tin for this material. We expose the light in the tin, and there will be droplets coming in, and every droplets from the tin get exposed by the light, and as you can see here, the light gets reflected and makes the EUV light. There is some problem with the EUV system because the EUV wavelength is very short, so it gets absorbed from everything. And because when we go through every pellicle, like we get reflected, we go through the pellicle, and there will be very low energy efficient. So there will be some problem when we make a pattern on the wafer. In the next class, I'm going to talk with the photoresist. We call it PR. There are positive PR and negative PR, and I'm going to introduce you about it. Thank you for watching my YouTube channel, and thank you.